In this video, I'm going to walk you through the post-lab analysis for Lab 9 limiting reactants. The first question on your post-lab is just the data that you recorded in the lab, the mass of the two reactants that you worked with, the mass of the empty filter paper before you used it, and then the mass of the filter paper with the product on it after it has sat and dried for a few days. The first calculation that you're going to do is to calculate the moles of each one of your reactants. So this is going to be a really simple gram to mole conversion for these two reactants. You'll do that using the molecular weight of each one of these. I'm going to put some random numbers in here. Let's say that we had 5 grams of FeCl3 and 5 grams of the NaOH. So there isn't a spot where you're required to show your work for this particular problem. For problem number 2, I'm just going to kind of squeeze it in here. So I'm going to do the NaOH first. Let's say that we had 5 grams of NaOH as our reactant. And you should, whatever your mass was of NaOH, you should have way more digits on here than 5. I'm just like trying to keep this video simple, but you'll have the whole, all the digits that you got from the balance. You want to multiply it by a gram to mole conversion factor. This conversion factor is determined by adding up the masses of all of the atoms in this molecule, the sodium, the oxygen, and the hydrogen. They add up to an atomic or a molecular mass of 40. So this would be the way that we would go about calculating the moles of the NaOH. I'm getting 0.125 for my fake data here. And for the FeCl3, we're going to do the same calculation, the same thing, although this one is a little bit trickier because what's up with this dot 6H2O. So this notation, this dot 6H2O, means that this FeCl3 molecule is hydrated with some water molecules. There are 6 water molecules that are stuck to or hanging around every one of the FeCl3 molecules. This is not enough water to make it look wet. So this is the dry product that you measured out on the balance. It's totally dry. It's not damp or anything like that. But those 6 water molecules that are in this compound, we do have to take them into consideration when we're calculating the molecular weight of this molecule. So when we're adding the molecular weight up, we're going to add up the mass of 1 iron and 3 chlorines and 12 hydrogens and 6 oxygen atoms, because that's how many atoms there are all together. And then we'll do that gram to mole conversion. We're going to have 5 grams of that FeCl3. I'm not going to write the whole thing down because it's big. And we're going to use the molecular weight to figure out how many moles we have. Now I'm going to just kind of do my best to remember these atomic masses for these different atoms. And I'm going to add up what I think the atomic mass is, or the molecular mass is. I'm not looking at a periodic table for this. So I think that the molecular weight is about 269 grams. And again, please don't use this number unless you've double checked and it's actually right. I feel like it's a little bit off. I'm just going by memory for the atomic masses of these guys instead of looking at a periodic table. You'll need to check that and confirm that for yourself. And that's going to give me, but that's somewhere in the ballpark of correct, whatever that 269-ish number, that's going to be in the ballpark of the correct molecular weight for this. So this tells me that's how many moles I have. And the next thing that we're going to do in questions 3 and 4 is to calculate the theoretical moles of the product FeOH3. We're going to do this twice, once based on the initial moles of the FeCl3 compound, and then once based off of the initial moles of the NaOH. Now, one thing that we're missing from this is a balanced equation. We can't calculate theoretical moles unless we have a balanced chemical equation. And so the balanced equation, I'm going to fit that in. I guess I'm just going to fit it in right here. The balanced equation looks like this. FeCl3, which you have aqueous, and NaOH, which is also aqueous. They are going to react together to make FeOH3. That's the solid, that's the product that we made here. and 3 NaCl, which is aqueous. And then I've got to do a little bit of balancing here. We need a 3 in front of the NaOH, and that looks good. So this is the chemical reaction that we're working with, and the FeCl3 is just a shorthand for that whole .6H2O. We don't need to include that in the balanced equation. We could, if we wanted to put .6H2O here, we would just have to add 6H2O on the right-hand side of the equation, and let's just like keep things simple and not write it at all. So for question 3, calculate the theoretical moles based on the initial moles of FeCl3. You're going to take your number from problem number 2, however many moles of FeCl3 you had, and you are going to do a multimole conversion. You want to convert into moles of FeOH3, converting from moles of FeCl3, and the conversion factors that you need are the stoichiometric coefficients from the balanced equation, 1 to 1. So that gives me, in my hypothetical data, I cannot emphasize enough, this is not real data. It's going to break my heart if I am grading somebody's lab and you're using these numbers. These are not real numbers. I will not mark that correct. We're going to do the exact same thing based on our starting moles of NaOH. So for my imaginary moles of NaOH, I had 0.125 moles of NaOH. And then I want to multiply this. Again, I'm calculating how much FeOH3 I have from how many moles of NaOH using the balanced chemical equation and the stoichiometric coefficients. 1 FeOH3 for every 3 moles of NaOH. 0.125 divided by 3 gives me 0.4167 moles of that FeOH3 product. So again, what I've done here is calculated the theoretical moles of FeOH3 from each one of these different starting reactants. Now I have to decide for my data which one is the limiting reactant. The limiting reactant is going to be the reactant that produces the smallest amount of FeOH3. So first step, I have to look at these two theoretical numbers. I have to decide which one is the smaller. That reactant is my my limiting reactant. So the limiting reactant, again, I'll say that one more time. Step 1, we have to analyze the 2 moles of FeOH3. We're going to decide which one is the smaller number. The smaller number, that is the one that came from the limiting reactant. There. Now, if you're comparing your data to somebody else in the class, you guys are not necessarily going to have the same limiting reactant. Limiting reactant varies person to person. So you might be like me and you might decide that the FeCl3 is your limiting reactant, but you might have a friend whose data is the other way around and their limiting reactant is NaOH, and that's perfectly normal. So don't be stressed about that. So then we are going to calculate our theoretical yield in grams based on our actual data. So to do that, we are going to focus on the theoretical moles that come from the limiting reactant. So we want to be ignoring all of this stuff right here because it's just a bunch of lies. We want to take the smaller amount of moles of FeOH3. For me, it was this 0.0186 moles of FeOH3, and we want to convert that into grams using a mole to gram conversion. And I'm going to kind of try to make up a molecular weight for FeOH3. I'm not super confident that I'm going to get this correct. So do not trust this 106 grams per mole. That might not be right. Please do not assume that this is a correct number. I want you guys to do some of the work on this. I don't want to do the whole entire post lab for you. And so this is going to be 0.0186 divided by whatever that, or not divided by, times whatever that molecular weight is. Again, please double check to make sure, actually add up that molecular weight, because I am almost 100% sure that 106 is inaccurate. This is the theoretical yield of the FeOH3. So Now we're going to calculate our percent yield. Our percent yield is going to be our actual yield divided by our theoretical yield multiplied by 100. We just calculated the theoretical yield, 1.9716 grams. We need our actual yield. And there is no place on this post lab for you to like write out your actual yield. There's no spot for you to figure it out. It's hidden in this data right here, the mass of the empty filter paper versus the mass of the filter paper with the dry product. Let's say that my filter paper with the dry product weighed 11 grams, and let's say that my empty filter paper weighed 8 grams. The difference between them is the mass of my product. So I've got 3 grams of product. That's my actual yield. I'm going to plug that in over here, multiply by 100. And as you can see, I'm going to get a high yield, 152%. This is nothing to be happy about. It's not possible to make more than 100%. So this, I can only make 1.9716 grams of product, and all of that extra mass is some sort of contaminant. In this particular experiment, this typically comes from not letting the stuff dry for long enough. But regardless of what it is, you're going to calculate your percent yield. And then the last question is asking you to identify which ions should be present in the solution after it was filtered. So let's just I'm going to draw a picture. It's probably not going to be great. Here's the Erlenmeyer flask. That's a really good looking flask. And here is the funnel. And oh man, that's a good looking funnel too. And then also you performed the reaction you've got like a beaker, and you've got in your beaker, you've got that liquid, that colorless liquid with the solid down at the bottom, which is like a brown color. Okay, so you poured that solution into the filter, and the filter captured all of the solid product, and the clear liquid traveled through, and the question is asking what the heck is in here, what's down there. You know that this is the FeOH3 solid. So let's kind of think about what's going on in here. In this beaker, you put into the beaker Fe3 plus ions and Cl minus ions. That was in the form of FeCl3. And you also put in sodium ions and hydroxide ions. That was in the form of NaOH. And you made the FeOH3 solid. If we kind of flip back to that balanced equation that I wrote, the other product of this reaction is NaCl. So that means that you have some Na plus ions and you have some Cl minus ions that are just hanging out in the solution, and they end up coming through the solution as well. So that it's not as simple as that though. So there's just kind of that part of it that like a lot of students will eventually figure that out, but it's a little bit trickier than that. So one of these two reactants was limiting. In my situation, the FeCl was the limiting reactant. And that means that all of the FeCl is going to be converted into products. So all of the iron that I put in is going to end up being converted into the FeOH3 product. The NaOH was not limiting, meaning that it was excess, meaning that not all of the NaOH got converted into making the FeOH3. So some of it was left over. The stuff that was left over is going to stay dissolved in the solution, and then will also pass through the funnel into the Erlenmeyer flask. So you've got to take that into consideration as well. I'm going to leave that for you to figure out based on which reactant was not limiting in excess. What else do you have present inside this solution?